The analog of classical determinism is a kind of quantum determinism. It's not deterministic in the same way because it involves probabilities. Probabilities for classical measurements. So it's not deterministic in the same way. But it's a kind of determinism, a certain kind of deterministic probability, as it were. And it is called unitarity. So all of these do have a quantum analog, and the quantum analog is not too difficult. What you'll generally see is that classical theories, the space of states, understanding what the space of states are, is really easy. It's really easy to know, to basically understand these first two, 0 and 1. Really easy to understand in classical theories in general. What's really hard in classical theories is the law of evolution for a system. In quantum theories, it's generally backwards. This is generically a very difficult question. What exactly does the space of states look like? How exactly do you configure it? Takes a lot of work. But the laws of evolution generically are in some sense simpler. So they're sort of reversed. But because the space of states, and because a particular state for a system is not a set, it's very hard to interpret what that means. And so, in general, there's a problem in quantum mechanics that it's not quite intuitive what the theory means. It does mean something, and it does mean something very specific, but you have to do a little bit of work to see what it means. In classical theories, there's no difficulty interpreting them. At least, not too much difficulty. One more note on time. You may say that, well, in special relativity, you may have read a little bit about special relativity and realize that it treats time and space the same. What could that possibly mean? Well, there is still a time variable which is treated in some sense differently than space. That time variable is called the proper time. It's written with a tau. Then there's another time in special relativity and general relativity, which is called the coordinate time. It is written with t. They are not the same in general. In fact, they pretty much are never the same. And essentially, proper time becomes the new parameter over which you evolve the system. Coordinate time for particles becomes another generic object, like positions and momenta and all that kind of thing. So these ideas are still fundamentally applicable to relativity. You just need a new sense of time called proper time. Now, what is a particular classical theory? What is the difference between that, which tells you what you need to have for a classical theory, and a particular classical theory? A particular classical theory answers those questions. It'll tell you, given a certain allowable system, a setup which is allowed by those particular laws of physics, it will tell you what the space of possible states for that system is. It'll give you a kind of ultimate generic rule telling you how to derive, how to give you the most generic space of states. In addition, it will give you a law of evolution over time for that system. And that law of evolution will always be such that it's deterministic forward in time, and it conserves information, which is to say it must be deterministic in reverse. And those are fundamentally what a classical theory gives you. So, first thing we're going to look at is Newtonian physics. Newtonian physics is the simplest classical theory that can model the universe. There are simpler classical theories, but in general they're not very useful, except for certain approximations, such as modeling a computer. But Newton's physics is kind of the simplest set of physical laws. Now, we're going to be talking about Newtonian physics for particles. We will get, eventually, to Newtonian physics for continuous objects. This is Newtonian physics for point particles. Now, what is a point particle? A point particle is an object which has no dimensions. It's just a point. Just a little dot somewhere in space. That's a point particle. It can have various properties associated with it, but it's just a point. Now, in general, what is the space of states for a point? Well, at any particular point in time, first of all, you need to know, where is the point? Where is it in space? What point in space is this particle occupying at a certain time? So the space of states for one particle has position. And that is a three-dimensional quantity in general. There are specific restrictions of Newton's laws when you only care about two or one direction of motion, that in some cases the other directions of motion are abstracted away, they don't matter, they don't contribute in any sort of meaningful way, so you can restrict it to lower dimensions. But for our universe, in general, position is a three-dimensional variable for Newtonian physics. So you need to know where the particle is. The second thing you need to know, too, is where is it going? You need to know, at any particular point in time, how the particle is moving instantaneously. It might be moving different at a slightly different point in time, but you need to know at that instant in time, what direction is it moving, and how fast is it moving in that direction. Now, that's a quantity called velocity. But there is a relevant quantity called mass, which enters into every classical physical theory. And so, rather than velocity for a particle, velocity is a three-dimensional quantity. It tells you, you can imagine a particle. Velocity is a three-dimensional quantity. It tells you how fast are you moving along the x-axis, how fast are you moving along the y-axis, and how fast are you moving along the z-axis. It's a three-dimensional quantity, and if you know how fast you're moving along the x-axis, how fast you're moving along the y-axis, and how fast you're moving along the z-axis, then you know in what direction you're going and overall how fast you're going. We will get to more specifics when we get to vectors, but essentially velocity is a three-dimensional quantity as well. But there is a certain physically relevant object, or physically relevant property called mass. And mass is relevant to every single Newtonian particle. It is something that always matters, and because it always matters, we never really want to know the velocity in isolation for a physically relevant system. What we really want to know is something called momentum. And momentum is just a three-dimensional quantity, and it is for a particle equal to mass times velocity. Now, the third possibility is additional quantities that participate in the dynamics. For point particles interacting gravitationally, 1 and 2 are all you need. But for additional particle interactions, such as electromagnetism, you need additional things, such as electric charge. So we'll just call these additional dynamic variables.